All right, continuing on with our review here, we've got question 2 from paper 2. Looks like a kinematics question. We see a velocity time plot before us, and it reads, the variation with time t of the velocity v of two cars p and q is shown in figure 2.1. Cars travel in the same direction along a straight road. Car p passes car q at time t equals 0. Okay, so right at this time t equals 0, car p here has passed car A. Okay, so it's moving with non-zero sort of velocity, and it just passes right by. But it looks like car Q here has a steeper gradient on this plot, which means it's accelerating faster, right? So it's getting to a speed of 30 meters per second, whereas car P, yeah, it started out faster, 20, but you can see like at this moment, about 8 or 9 seconds after the car P passes car Q, they're going the same speed, and then car Q is going faster. So remember, we're looking at velocity as a function of time. It's not like the moment that he overtakes him, he's got to pick up speed, and there might be more sort of ground to cover there. Maybe that's what we'll have to calculate. I don't know. It says the speed limit for cars on the road is 100 kilometers per hour. State and explain whether car Q exceeds the speed limit. So that question is basically extracting this data off of the figure, realizing that car Q achieves a speed of 30 meters per second, and then comparing it to 100 kilometers per hour to say whether or not that's faster. Okay, so we got to convert meters per second to kilometers per hour, and then go, well, is 30 meters per second faster or slower than that? Did the car exceed the speed limit? In order to convert meters to kilometers, we recognize that there is 1,000 meters in a kilometer. In order to convert seconds to hours, we're going to put 3,600 seconds per hour, like that. And if we look at the way that I've set up this calculation here, we got 30 times 1 times 3,600 divided by 1,000. So it's really just 30 times 3.6, right? Those two zeros, 36 divided by 10, so 30 times 3.6. So it's pretty close, right? 30 times 3,600 divided by 1,000. So we realize that this 30 meters per second corresponds to a speed of 108 kilometers per hour. And you would want to sort of put that into words, because anytime it says and explain, make sure you're doing that. It's like, it exceeded the limit. You say 30 meters per second is 108 kilometers per hour, which is faster than 100, so yes, it exceeded the speed limit. Make sure you're and explaining anytime it asks you to. Calculate the acceleration of car P. All right, so car P is sort of the other line there, and acceleration, you may remember, is the gradient on a velocity time graph. It's pretty tough, especially when you're sort of, don't have the paper in front of you, sort of working off the screen up there. But P goes all the way up to this one. Here's 20, here's 30. There's 10 lines in between. So each, square is 1, 21, 22, 23. So that's 24 meters per second. Acceleration, V minus U over T. Note that that's the rise and that's the run. If, like time 1 is 0, then it's kind of like T2 minus T1. But if T1 is 0, then you can just sort of think about like V minus U over T, like if the initial velocity corresponds to a time of 0. All right, so we've got for this one, the final velocity 24, the initial velocity 20, and that change occurred over 12 seconds. So the acceleration of car P is just going to be 4/12 or 1/3 or 0.33 meters per second squared. Right? We just sort of do that working by extracting the initial and final velocity over the time on the graph. So car Q is exceeding the speed limit because 108 is more than 100, and car P is accelerating 0.33 meters per second squared. Determine the distance between the two cars at time t equals 12 seconds. Okay, the distance at the time t equals 12. How are we going to figure that out? So we know they're at the same position here at time 0, right? Because that's when car P sort of passes car Q. The area underneath this curve gives the displacement, right? And so car P has all this area here. Car Q has the area of sort of this triangle. And we want what the distance between them. So if we calculate each of their displacements and compare them, maybe it's the same. Maybe there's no distance between them. Right? So it's not obvious looking at that. You know, maybe you've got some, well, it kind of is actually. Car P looks like it's covered a lot more ground, right? Because you've got like all this area here that's not going to be in the area calculation. The only part of the area that Q has that's not like part of P is like this little bit up here, right? So upon inspection, you should see like, well, car P passes him at 20 meters per second. And even though car Q eventually goes faster, because it started out at a speed of 0, I don't think it's covered, you know, as much ground. But let's quantify that thinking. So the area underneath these curves gives the displacement. You could also use your equations of motion. Remember, we derived the equations of motion by considering a plot just like this one. For example, this shape here is a trapezoid, right? So we've got a rectangle and a triangle. We could calculate sort of the areas of each and then add them up. And in doing so, we'd be calculating the displacement. So it's like the initial velocity times some time plus the 1/2 at squared. And since we already know the acceleration of this, we could use that equation to solve it. In other words, the area of this triangle is 1/2 base times height, and the base here is at, because it's the difference, you know, v minus u equals at, because a is v minus u over t, right? So we can kind of see that the base of this triangle is the quantity at, and the height is t, and that's where you get the 1/2 at squared. So this is actually one of the big 4 equations of motion, and it actually just comes from taking the area, you know, underneath that curve. But it may be easier for you to just think about, oh, well, let me just sort of pull out the data, you know, like the initial velocity was 20, the acceleration was 0.33, you know, that we just calculated, rather than thinking about it like a geometry problem. A geometry problem would kind of look like this. The area of a trapezoid, which is a crudely drawn trapezoid there, is 1/2 base 1 plus base 2 times height. And so maybe you want to solve it that way. 1/2 the base here, 20 meters per second, plus the base here, 24 meters per second. And then the height would be, let's see, so that's the base, that's the base. So the height is the time, 12 seconds. So this would be meters per second times seconds. And so meters, you know, displacement. So that would be just the distance that car P has traveled, right? It's a trapezoid. We need to use the area of a triangle for car Q over here. So we'd say the area, you know, for Q, 1/2 base times height, 1/2 12 times 30. So this will give us the distance covered by Q. This will give us the distance covered by P. And I bet you this number is bigger than that number, and by how much will be the answer to our question. While we're at it, we should just sort of realize that if we plugged in 20 times 12 plus 1/2 0.33 times 12 squared, that number should be the same as this one, right? Because they're solving for the same thing. It's not immediately obvious, but let's hope it works. So we got 20 plus 24 divided by 2 times 12. 264 meters. The same thing over here, 20 times 12. So 240 meters because of the fact it was already moving at 20. And a little bit extra from the acceleration there. 0.5, 0.33. You get like another 24. Sure enough, the answers agree, right? So this is using like an equation of motion, which comes from, area of a rectangle, area of a triangle, area of a trapezoid, same thing, right? Don't forget your area of a trapezoid equation. You never know when it will come in handy. And then the area of the triangle over here. So we've got our 12 times 30 base times height, but it's a triangle, not a rectangle. So we got to cut it in half. And so we realize that car Q has traveled 180 meters. So if car Q has only traveled 180 meters, while car P has traveled 264 meters, 264 minus 180, 84 meters. So that would be the answer to the distance between the two cars at time t equals 12 seconds, 84 meters. It says from time t equals 12, the velocity of each car remains constant at its value at t equals 12 seconds. Determine the time at which car Q passes car P. All right, so that's going to be a little bit tricky there. So we know that there's 84 meters sort of between that. We just calculated that. The time t at which car Q passes car P. So if car Q is traveling at 30 meters per second and car P is traveling at 24 meters per second, so I think what we want to do here, okay, determine the time. So let's think about, there's probably a lot of different ways to sort of get to the answer here. There's maybe a more efficient path to it than some other ways. So car Q is going, we don't have acceleration anymore, right? So the velocity remains constant, so it makes the physics a little bit simpler in that regard. Let's say that velocity is distance divided by time. So time is distance divided by velocity. If we take 84 meters divided by 30 meters per second, right? And we'll have the time. We'll take 2.8 seconds for a car that's traveling this fast. But see, so now I think we're gonna have to set this up a little bit differently. Car T over there going 24, so 84. A car that's going 24 meters per second for 2.8 seconds. So we need to actually make them when the car passes car T. So the distance, we want to set it to be the same. So it's kind of like the displacement equals velocity times time. And we have to cover 84 meters. But how much more distance is the other car going to pick up too? So we have to sort of compare their rates here. What's the best way to go about this calculation? I'm going to puzzle over it for a moment or two, and you can do the same thing. Yeah, I think that might be the best way, is to just consider, well, this one's going 6 meters per second faster. And so 6 meters per second covering 84 total meters of distance is going to take a time of 14 seconds. Okay, so it takes something that's going that much faster, 14 seconds, to sort of make up the ground. And that way you're sort of saying, well, they're each going to sort of still, pick up ground, but that's the sort of the difference between them and the ground that we got to make up. Now, 14 seconds is not the answer to this question, though. It's very tricky because we already are at 12 seconds. And the way that they assign the time here is by saying from time t equals 12, determine the time t. Well, time t, we already have 12 seconds that's elapsed, right? We solved for the extra time it would take the car Q to pass car P. So the final step to this is, like, once we realize that it's going to take an additional 14 seconds, is to add the 12 back into it. So the total time is 26 seconds. At time 0, car P passes car Q, right, and covers a lot of ground, but car Q has a faster acceleration, right? In other words, it reaches a faster speed. And so it's only a matter of time before the two are going to be even again. And that total time from the time where they were even, time t equals 0, to the time where they're even again, is 26 seconds. It took 14 seconds, sort of after they reached their top speed, for the faster car to pick up or to gain on the car that was moving a bit slower. All right, so we eventually made it there. Now we could keep going here, keep a good thing going. Take a look at question number 3. Looks like some differences between stationary waves and progressive waves, but maybe we'll save that for another day. This is Dr. Schleich with the Physics Live. See you next time.